Hello, everyone. I am Olivia Sobek, and I am going to be sharing my research through the Robotics Institute Summer Scholars Program at CMU under Professors Zeynep Temel from the Zoom Lab and Melissa Orta Martinez from the Shred Lab, as well as mentioning my mentor, Sydney. And I will give you a little backstory to my project through the intro. Basically, exploring rough terrain following a natural disaster poses significant safety risks to humans due to unstable environments. To address these challenges in inaccessible areas, we are developing centimeter-scale spherical robots called rescue rollers, in collaboration with a team working on inflatable vine robots to achieve these goals below. And then basically I will talk to you about my goals. There are three main goals. The first one is developing a mechanism to allow the robot to transform from a spherical compact shape to one capable of maneuvering through challenging landscapes, which I will go into more detail later. The second goal is testing force produced by each wheel, including push and pull across various terrains to effectively collaborate with the vine bot, also understanding different wheel geometries under varying conditions. And the third goal, designing a flexible PCB for wireless charging and maintaining enough charge to cover long distances, as well as understanding the power distribution of the system. So going back to the first goal, part of my project was designing a prototype mechanism for the spherical bot. Basically, the bot is a ball, a sphere, and whenever it unlocks by rotating the motors, my mechanism will essentially pop it out, so that way it deforms from its shape and it's able to roll around obstacles or go over, possibly. And so basically, my idea with the first one was having a basic 4-bar linkage system. So there's like linkages, there's spring, which would essentially pop it out. And basically, the issue with that was it would get bunched up, which could be a later issue, like it getting stuck. So we then thought of the next great idea, which what if we add magnets and organize them in a way that they would repel? So basically, whenever the ball is compact and together, whenever it unlocks, the magnets will repel each other, so it'll pop out. And so that's what led to the final design. And yeah, so moving on to basic behavior experiments. Another part of my project was testing force produced for pushing and pulling across various terrains. First part was looking at the oscillation of the wheels. Some wheels would have a lot of spikes in the data. And so from there, you could make observations. Like some have more stable, some are less stable, like looking at the triangular edge, that's less stable. And yeah, later on, I found out that wheels with a more stable oscillation generate a higher average force. And then moving on with the data, we ended up adding different terrains like a turf, rocky surface, acrylic plate, which was actually quite slippery for the wheels, MDF, which was more like a scratchy type of surface, and then MDF with life grip tape, which has a more rough surface in the MDF. And basically, after testing each wheel on all those surfaces, I concluded from the data that the concentric wheel produced the highest average force, and funny as it is, also the most stable force compared to all the wheels, which by looking at this data, we can use to finalize the actual wheel design for the bot. So we can use that concentric shape towards the finalized design because we want to produce a higher average force. That way it's able to go past obstacles or interact with the vine bot. Moving on, with circuitry to operate for prolonged periods and cover long distances, the robots require charging to sustain their performance throughout rescue mission. For the vine bot to maintain a soft, flexible texture, a flexible PCB is essential for transmitting power. And as you can see in the photo, there is the flexible PCB next to a quarter. It's very small. We try to keep it as small as flexible as possible. And Yeah, basically the reason why we need it to be flexible is because a vine bot, it's like squishy and it's inflatable. And so we don't want a hard PCB to attach to it. We need a flexible one to adapt to its like skin like appearance. And a good question might be, oh, why do we need a wireless PCB specifically? Why can't we use a wired? Well, when these robots are going out in an unknown environment, we don't know how long the distance is. Maybe the distance is longer than how long the wire is. So in that case, if we don't know, we should go with a wireless charger. That would be the most optimal uh, reasoning to go towards. So that is why we went with that route. We use coils. I'm using an online design software called Easy EDA to make this PCB. And yeah, moving on for future work. Basically, hopefully we'll finalize a wheel design in the future. Maybe adding a jumping tail mechanism, which if it's stuck near a rock, we can use that jumping tail to jump over the rock, which would be cool. And a coupling mechanism to apply power electronics to the robot itself, and maybe integrating sensors. So say if it went in an environment where they had bad air quality for humans, well, we would need a sensor to prove that. Anyways, thank you so much for watching this video. Thank you to Riz and the Zoom and Shred Lab for having me this summer. With your support, I get to pursue my passion of robotics and learn more about in-depth applications to real-world problems. This work is supported in part by the National Science Foundation grant. Thank you. Bye.